All right, Unit 2, Energy and Momentum. That's what we're on to today. So it's Chapter 4 in your digital textbook there. Looking at work and energy, and as you've probably noticed, we're going to continue this way in the course, where we're going to be doing some review of some grade 11 stuff, and then with some grade 12 twists or additions to it. And so that'll actually continue here. Mostly just this calculus idea link as an extra, but I mean, otherwise, we're looking at work and energy, same as in grade 11, really, just a chance to review it. So, but we'll get into momentum, which definitely wasn't covered in grade 11, soon in this unit. So here we go. Main thing to review here is that work done is a change in energy or a transfer of energy. So W and delta E mean the same thing, right? Work done is a transfer of energy. It can add to a system or it can take away from a system. So it can be positive or negative, but it's not a vector. You're never going to be like the sine and cos of the angles and so on, just so you know. And work done from grade 11 was just work done equals force times distance, right? So in grade 11, we just treated those as scalars because we didn't have any grade 11 topic included about multiplying vectors. So we just said, the scalar versions works good enough. We're pretty much doing the same thing in grade 12, but it's a little higher tech, if you will. And the logic is still very much the same. You know, you have only the component of the force in the direction counts or contributes to work done. And so, you know, just like in grade 11, we do the component like this. And so, but for grade 12, like we're going to get that same answer, okay, in grade 12. But for grade 12, what we're going to do is we're going to say, okay, we have this special definition for multiplication of vectors, and it's called the dot product, and it's shown with a dot. And so the definition, it's like a mathematical definition. Math class, you know, math people in math would think of it as a mathematical definition. I'm all over the place here, Lori. So page keeps switching on me. Why? Page just switched on me a couple of times for some reason. I think maybe the smart bar might be slightly out of alignment. I'll use the mouse here so it doesn't do that again. And so, yeah, in math class, you think of it as like a way or a method or a definition of one of the ways you can define multiplication of vectors. And so it's defined mathematically as the magnitude of each of the vectors multiplied together with the cosine of the angle between them. Well, if you look at the grade 11 version of things, you've got the force and the angle to the direction that it's traveling, right? And so, you know, the component, the x component in the direction that it's traveling is f cos theta. And so you can see that, you know, F force times displacement becomes, or force times distance, just scalar versions would become the magnitude times the cosine times the displacement, right? And so it's the same thing. Long story short here, right? It's the same thing, just a little more technically defined, if you will. Yeah. So that is that. It's interesting. I find it interesting that you know, in a math class, when I learn about dot product, it's, you know, very much talked about. It's just like a definition. There's two ways you can multiply vectors. One's a dot product, and one you'll see later in this course is called the cross product. And they do look at some of them applications in a math class, but they think of it really as like a defined way. Like we looked at it and we saw vectors and we thought, how could we multiply these? And so we defined this as one of the ways, and then they show applications of it. I don't think it really happened that way. I think it really was like, you know, an obvious thing from physics where you have the force in the direction, and so the idea of the magnitudes times the cos of the angle was born really out of the physical concept that we're looking at. So here's an example. We got our 10 Newton force acting at 15 degrees to the horizontal, causes it to move forward 2 meters, calculate the work done. So it's usual stuff, right? Except now we can start with our grade 12 definition of F, you know, force vector dot product with the displacement vector. But it quickly becomes essentially the same thing, right? I don't actually kind of prefer this one, to be honest. It's just I'm showing it to you because, you know, it's going to extend to other things. You know, if you look at the grade 11 version where we're saying the force in the direction, the component of the force in the direction, you know, it's a little more intelligible, if you will. It's a little more obvious why it makes sense. So my preference would be that the green version there for sure. But, you know, both work. They mean the same thing. So with the units here for this, review from grade 11 likely, you've got your force times your distance, so you have newtons times meters, and then newtons is mass times acceleration, and so we have kilograms meters per second squared, and it gets multiplied by meters, and so we end up with kilograms meters squared per second squared as like the fundamental meters, kilograms, seconds version of the unit, which is actually a unit of energy. Okay, and it's called the joule. So we should add on here that it's energy, and the unit is the joule. All right. So the idea of positive and negative work, just like you saw in grade 11, really, the idea that you can add to the system or you can reduce the energy of the system. And so if you think of the total energy of a system, if you're adding work in, then the total energy of the system increases. You have more energy in the system than you had before. So what energy did an object or system as a whole get in the previous example? So in the previous example here, we had the object that was moved 2 meters forward while pushing on it, and so it contributed 19.3 joules of energy. Well, what does that look like, right? What kind of energy is that? Well, if there was no friction, then that force would have been causing an acceleration, right? And so if it's accelerating, then we could figure out that it's going to be gaining velocity, of course. And so really we're thinking of it as kinetic energy, right? That's what is added to that system, kinetic energy itself. Right? So yeah, adding, now you have more energy in the system. Look on the left side, because you added energy in, and now you have an extra, whatever amounts of energy there were, now you have this extra amount of kinetic energy. If it was sliding at a constant velocity due to some opposing force, let's go with friction in this case, right? Then it would actually, that energy would go to heat, right? Friction just dissipates heat to the surroundings in a scenario like that. And so, the same kind of logic would exist, except it's thermal energy that's, as part of the overall system, at least anyways, right? Kind of escapes to external parts of the system and seems kind of like it's lost, and you'll learn about that or see that again shortly in another lesson. If the force was causing it to slow down, well, that would be reducing kinetic energy, right? If the force was going against the motion, causing it to slow down, you can think of that as a negative work done and a reduction in the total system energy. Okay, so here's the part I said we're going to see later, the law of conservation of energy, right? So the law is that energy cannot be created or destroyed, right? It can be changed between forms, and it can seem like it's lost, right? If those forms aren't super noticeable and they're, you don't notice them in the surroundings around you and so on, those other forms of energy still do exist, even though they're not super obvious. And I didn't do the balloon stretch video yet, but I will do that and just link it somewhere. Anyway, so yeah, the energy can go to the surroundings. This part on the side here is for later in physics, but energy can't be destroyed. It can change different forms. It can seem like it's lost because it goes to the surroundings. You don't really see it anymore, but it still exists. That heat motion, that thermal energy is still out there somewhere. Energy can also be borrowed, just not for very long. And it turns out that there's a proportionality constant between how long you can borrow energy and how much energy you can borrow. And that's what, if you ever looked into this, it's called the Heisenberg uncertainty principle. And the proportionality constant is h bar. And we'll be able to measure that later in this course, the actual quantum mechanical property of world, one of the quantum properties of the world around us. We'll get to that later, though. But yeah, your key concept here would be that your energy in a system is if you're looking at the complete system, then it's constant. So then in the previous examples, it would, I would include myself as the universal system. Like it's so when I said you get extra energy, really that energy was there, it just transferred into this system, right? And I don't know if you want to think of it like that. But an example of gravitational potential energy converting into kinetic energy as it falls. Like we'll see that soon. The idea that you can have transfer between one form to another. And yeah, I guess if you included my chemical potential energy that I have from having eaten lunch as part of the whole system, that it's obviously just switching to kinetic energy for the object that was pushed and so on, right? Another little thing of review from grade 11, that the area under force displacement graphs is really force times distance, so it's work done. So this is the grade 11 version where, we looked at that as something that is definitely part of the course. We can do it. You just get the area underneath the curve. It gives you the work done, right? For a constant force like the 10 newtons for the full 5 meters, that's just, work done is force times displacement. It gets a little more complicated when you have the increasing force. In this case, it was increasing linearly. But the only extra complication is the idea of an area of a triangle, right? So very doable. The next level, grade 12 version, and I mentioned it a little bit in my grade 11 class, but if you had a non-uniformly changing force value. And so how would we estimate the area? Well, one way you could estimate the area is by just drawing rectangles underneath it. And the idea would be that, see how you have a little extra and a little less included each time? Those kind of balance each other out for the most part, and you'd get a decent approximation. You want an even better approximation? Well, then you break it down into even smaller numbers of rectangles, even more rectangles, actually, even smaller width, but even more rectangles. Because now the amount you're including and excluding by accident are much smaller, and so in general, they're going to cancel it even better, basically, right? The idea is, of course, you just add up all that area, whether you're just adding up a bunch of rectangles, and you get an idea of the value. Now, I didn't quite talk about the calculus part yet, so I'm going to delete that. The calculus version of this is that we can actually, it's called integral calculus. So you don't see, it's not officially in the high school curriculum anymore. They've removed it, and I guess you just get to see it in university for the first time. Although I know from personal experience of people I know that have gone to university, it's assumed that you've seen it before, which is unfortunate. So if I was teaching a calculus class, I'd probably give a really good intro to it, let's just say, even though it's not officially in the curriculum. But calculus has the power to turn this concept of estimating the area into exact numbers of what the area would really be. And what it does is it gives you a method for doing this, like reducing the number, the width of the rectangle, so increasing the number of rectangles to a large value. So you think about it, if you decrease the width of the rectangles down to 0, you'd have an infinite number of rectangles. You'd have no extra or excess included by the rectangles at each spot. And so you could add them all up and get exactly the area. And that's the concept of the integral calculus, right? You add up, this is the symbol for adding up, all of those rectangles, and you let the width of the rectangle go super small. So you get a whole bunch of areas you're adding up, and it really does give you the value, right? Well, the neat trick about calculus, if you've taken the calculus class already, the calculus in Ontario does include the idea of the slopes. Okay, so this is the math trick about getting the slope, which is called the derivative, and that gives you a mathematical value, exact value for the slope at an instant, rather than looking at a curve and saying, okay, well, this tangent has this slope, and then this tangent has this slope, and then this tangent has this slope, and eventually you're approaching the tangent slope at an instant, right? That's this. And that does that for you mathematically. There's an equivalent version, the exact opposite process, but it's the equivalent mathematical accomplishment of getting an equation which will give exact values for areas. And it's called the integral. So, it's a bit of a spoiler alert, I suppose. You see in calculus, you learn a long-winded way of doing this that's very obvious about what it's doing. It's really this idea of approaching and so on, formalized. And then eventually you get the trick, the mathematical trick, that x squared can just become 2x, and you'll learn about that in calculus if you've taken it, if you haven't taken it yet. And if you have, you already know the trick, you agree with the result there. The opposite process is just called the integral. And so you work backwards and say, oh, well, this is what we must have started with. And so again, in the integral calculus uh, review from a calculus class or seeing it full on, leads you to the idea of that mathematical process. Anyway, so long story short, it gives you the area under the curve. All right, so yeah. So the main that I did put in here, by the way, that integral calculus idea, and that it's for interest only. It's to give you some experience with the ideas of it, so that when you see it, it'll make more sense to you. Not for testing for this class, but this idea, could be, of course, right? Yeah. So we did questions like this in class, how much work was done and so on. I should mention too, there's questions here about, in what kind of situation do you not have any work done? I didn't mention it as much at this, didn't mention it yet here actually. But if you're pushing on something but it doesn't move, then no work was done. Or if you, if there's no force, then there's no work done. Yeah, so just watch for that in the questions in the practice assignment. And let me know if you need any help. All right. Till next time, thanks for watching.